to such an important meeting.
Welcome.
Okay, dear participants, welcome to our third and last keynote speech session. I would like to introduce our keynote speakers to you. Our first keynote speaker is Dr. Lilia Halim from Malaysia. Dr. Halim is a professor in science education who has research interest in pedagogical content knowledge, innovative thinking in science, for example, STEM, especially in STEM, and non-formal science learning in Malaysian context. She is also expertise on the various national and international organizations. And our second speaker is in this session is Dr. Raquel Mamluk Naaman. She is employed in the chemistry group at Department of Science Teaching at the Weizmann Institute of Science Learning, where she was the head of the National Center for Chemistry Teachers for 16 years. She is also coordinator of chemistry teachers program in framework of the Rothschild-Weizmann program. She was also the leader of the various projects in the European Union based. Now I would like to give Dr. Halim the floor, or in this context, the microphone. Dr. Halim, are you here?
Yes, I am here. Thank you.
Okay, thank you for your speech, and you can start now. Thank you.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and good evening. It's from Malaysia. It's 6 p.m. around 6 p.m. Thank you as well to the organizing committee for inviting me to share our some work that we have done on SMET. So thank you, Prof. Salih. Nice to see you online.
Nice to meet you.
Yes. Okay. All right. I hope this is on your screen now. I'm sharing the PowerPoint slide. Is it on your screen?
Yeah.
Everybody? Yes.
Yes.
Okay. Right. So I would like to share with all of you our work in Malaysia on the topic of integrated SMET, a Malaysian perspective. And if we go to the next one, the presentation will be based on these four sharing points. I would like to talk about a little bit on how STEM education is conceptualized in Malaysia, and then what is SMET education in Malaysia, and some research findings that we have done specifically on SMET education, and some reflection on the work that we have done. So SMET education in Malaysia, it was introduced in STEM education in Malaysia, it was introduced in 2013. As we know, there are various conceptions one define STEM. It falls into a continuum as shown in the diagram. So when some people talk about STEM, it is about a science class without any of the other STEM components. That means 4 disciplines operating independently. And as you go further up to the continuum, as long as there's integration of 2 other disciplines, it's called STEM 2.0 in this case. And if you have three integration of the discipline, it goes 3.0, and a fully integrated one, we have all the other components of STEM components, and it's called integrated STEM. So what this shows us is that even though we are going towards integrated STEM, but there is a reason or a concern of also enhancing the interest in the specific discipline itself. So there is a case for doing STEM 1.0 even up to 4.0. So in that case, in that scenario, in Malaysia, we conceptualize STEM at the school level to be as STEM as a field, meaning as a discipline on its own or a combination of a discipline. STEM as a stream, that means students enrolling in upper secondary school, when they choose 2 or 3 more disciplines in STEM, they are in the stream of STEM, and this is for the reason of our undergraduate programs still accept their requirements are still based on whether the students have achieved certain grades or certain levels in the specific discipline. But we also acknowledge that STEM is also an approach. An approach here means it is done through a pedagogical strategy. As we know, it's either project or problem-based that involves design-based activities and in real-world settings. So we operate on all levels of STEM combination. And in a systematic review of 23 research on integrated STEM education, there are principles, and I think people would agree that these are the 5 components of principles for an integrated STEM that first integrates all components of the discipline, science, technology, engineering, and math into one learning experience. Use project-based or problem-based, involves inquiry, and it's problem-centered. It also reinforces that it should be in real-world application, and towards developing soft and technical skills, as well as preparing for careers in STEM base. So then I would like to move on to the concept of SMET. SMET, E here refers to entrepreneurship. My colleagues and I, we have been working on this area since 2005, in which we were basing it on the policies of science and technology in our country, in which we were going towards being a high-income society. And being a high-income society means that we have to be involved in industries that develop science and technological products that are innovative and creative. And in doing so, it will be involving a convergence of creativity, innovation, and to some extent, entrepreneurship. And this new model, economic model, has been an idea advocated in our policy of science and technology. So that's where we begin our work on the SMET education. A little bit theoretical background to the concept. We know we have academic scientists in a university, and as an academic scientist, they do not venture into commercialization. To some extent, some do, and if they do, they are considered as technology producer. But for this creative economy that hinges on innovation, is what we should be aiming for, is to produce scientific entrepreneurs. And how do we define scientific entrepreneurs? Or in this case, by Peter and Ann, their work in 2000, they have coined this term, scientific entrepreneurship. It's the process of producing innovative science-based products based on the ability to envision new products in a presently non-existent markets. First, it says it is scientific-based products, and it has to be in a presently non-existent market, the product, so that, in other words, is to create a value add kind value. The product has to be value added to the existing existing form of the product, whatever the product will be, or system or opportunities. So we have gone through the literature, and there are various approaches to this. Either we develop the personal characteristics of the successful entrepreneur, scientist entrepreneurs, or we develop academic programs. We have looked through some of academic programs that have entrepreneurship together with science, and is usually at the master's level in various parts of the world. However, the academic programs are more focused on only on the technical aspects, meaning how to do a business proposal, how to do a joint venture kind of papers. But we were doing at the school level, and we thought that it would be important to inculcate a thinking process that would go towards developing being a scientist entrepreneur. And we were targeting for the formal education, for the curriculum, so that it's being inculcated systematically, and everybody has a chance to be involved in this thinking process. So at that time, we were thinking, actually, we were doing some kind of integration already, even though there was no engineering explicitly, but there was, as we will see in the next table, there was a kind of engineering design involved. But the model of integration that we were drawing upon was by Davidson, Miller, and Mathney in 1995. And there are many ways to integrate a discipline. Either is based on specific discipline or content, or in fact, if you're talking about just the process, or it could be a methodological integration, as shown in this slide. Or what we usually do is through thematic themes to teach a concept around a theme. So we decided to take the process as our basis for our conception of entrepreneurial science thinking, and it's shown in this table. We were, as I said earlier, we were going towards creating or innovating existing product, and that will be involving design, and also it would involve problem solving. So the column on science process is, well, we have many definition of what a science process skills, but these six processes that's being tabulated are the more general one. And it's being used in Malaysia, in which we start with observation. We believe in the science process skills, observation comes along. Entrepreneurial thinking is also, they also have this concept, which is observation, but for different, they have same functional skills, but for different purpose. For example, in science, we observe the natural phenomena, but entrepreneurial thinking is observing the phenomena, but for the reason of trying to create new ideas. So that's where there is similarities in function, but also there's differences. So what we did was to combine these two, the nature of process thinking of these two disciplines, and we conceptualize as for entrepreneurial scientific thinking. The students have to take in purpose initiative, observe purposefully, deliberately, and continuously. As I say, it's not only to observe the phenomena, but to find what will be, how to innovate further of the phenomena that's been observed. Okay. Then we have describe the phenomena, describe the need. So they are all, they have similar functions, and we combine both, and we come up with another thinking element that should be in the entrepreneurial science thinking, that is keep thinking to find uniqueness, difference in the phenomena that's being observed in a form of new ideas, system, or product, or model, or techniques. And we go on to the steps where the blue one also shows some similarities and the differences that we combine. And what is important in this conception is the final one is it's not only to create products, but to have a value add ideas to the products that's being developed for the society and the community. So this is the extension part of science process skills, as well as entrepreneurial thinking when we combine both thinking processes to develop this entrepreneurial science thinking. So based on this conception, we are saying that based on science and technology concepts as well as knowledge, together with creativity and innovation plus entrepreneurship, therefore entrepreneurial science thinking will meet the policy that I've said earlier, in the sense to develop science entrepreneurs going towards creative economy and towards innovative science-based products which has value add for high income society. So in doing that, we realized there is another concept that's quite similar, and it will probably support to the entrepreneurial science thinking. And this concept, I think some of our colleagues here would be very familiarized. It's called scientific creativity. And it's actually a trait or ability, again, that's needed to potentially produce a product that is original. And original here we could also consider as being innovative. And what are the traits? First, being fluent, meaning the student is encouraged to give various, many numbers of original ideas. That means generating several ideas. At the same time, being flexible. If they are bound to find something that's blocking, not working effectively, they should be able to change or generate ideas from from another perspective. And of course, originality here is where it will bring to producing a product that is more innovative. So according to this model by Hu and Eddy, these traits can be developed, and in the process, it will ask the students to think and to imagine. And the product that they were referring to is not only a technical product, but in other forms, probably a scientist would require, like producing a new scientific evidence or solving the problem shown in this three-dimension model of scientific creativity structure. So we found out there are some similarities and differences between STEM and SMET. I think the similarities are obvious. First, both are using context-based problems, real-world problems. They employ problem and project-based as well as design-based learning, and involves inquiry. But the main differences from STEM and SMET that we are operating in Malaysia is that in SMET, science, maths, and entrepreneurial thinking and technology, we begin from the science concepts, because sometimes STEM, when the focus is on engineering, they were more focused on the techniques rather than the science concept. That's one. Second, SMET does not have to be based on problems. We don't have to wait for problems to happen, because if we wait for problems to happen, there won't be any innovation. So even though the product is functional, as an entrepreneur, as scientific entrepreneur, innovation needs to go on, and therefore the thinking must be done despite having to solve any problem. So that's what he meant by not necessarily based on solving problems, but you could start by just looking at something and think about how you could innovate the phenomena further. And again, the main difference is that it has to be whatever product or artifacts or system or technique that's being suggested has to have a value creation and practicality. So these are some of the similarities and differences between STEM and SMET in our view. So here are some findings from how we inculcate our conception of entrepreneurial science thinking in the form of in the teaching and learning. And we base the thinking processes as shown in the table by observing, asking the students to observe purposefully, get involved in the thinking to find uniqueness, select the one that's being innovative, and improve or design the product, and ensure that the outcome has to have a value add to the existing ideas or products that they are trying to innovate. One criticism probably is this hierarchical, or is it linear? No, but to inculcate something new, this will be a first step to inculcate it analytically. But because one could start from any part of these processes, but for the purpose of a new way of doing it is to have it step by step, linearly in this sense. So this is a context. We have to give a context on what they are supposed to do, and in this example is they are to design an electronic device that uses the source of energy, alternative source of energy, because this is done among 14 years old student, and they are to imagine and also to design. And this is just one of the activity sheets that we have in the module, and this is the first step they need to think about by paying attention and see how sources of energy are produced, and how the current sources of energy are being used in this case, the handphone device. So these are some of the worksheets in which it will encourage them to generate ideas. And here are some of the outcomes. Here is done among 14 years old students to design. In this case, it's like a laptop, and it's a simple design, and then having solar panel there, okay? And then we have, this is just their imagination of producing a device in the form of a pen. It does not only for communication as a handphone, but in the form of a pen, and they have other function as well. This is what the ideas the students suggested based on that thinking processes, and this is another design. They don't produce product, we just ask them to imagine and to design. So what we found out was that these are the factors that facilitate such thinking, in which students are able to be imaginative or creative, not just by just observing the environment, but getting more input and other information through other sources like reading the book or the web and so on. And by encouraging visits to scientists, doctors, or engineers, those are in the field, will help them to have a better idea as well as to innovate. And it all depends on the vision of the school as well as the learning environment that the school provides in the sense of encouraging them to be innovative and creative. Then we talk about how about the teachers involved in this. So the pedagogical content knowledge of EST is also being researched on. And these are some of the feedbacks we got from the teachers. What we can find that they were impressed that students were able to generate information, because our teachers sometimes very focused on classroom teaching, but they find it actually these activities are able to invite the students to think critically and creatively. And teachers realize that they need to have good content knowledge in supporting their students' creation based on scientific knowledge and some contextual knowledge in which in doing some innovation, they need to know their surrounding so that the innovation is relevant to the community. So this is how Malaysia does in terms of formal curriculum. They have a book that gives guidance to the teachers on how to inculcate a STEM approach. What I'm trying to show here is that there is some element of entrepreneurship in the process, especially when they were asked to improve the artifact that's being asked to innovate. So that's some element, and this is a rubric on how they go about evaluating the outcome of the innovation and the product being developed. So as I'm coming to my last two slides, as for discussion, pedagogy that is problem-based, project-based, and allow risk taking for the students, be able to see failures, very important if SMET is to be inculcated. Of course, teachers have to be ready and aware of this concept, and that can be inculcated in the formal and non-formal learning environment. Teachers themselves, in terms of knowledge, I think there's a reason also that we could look into their scientific creativity, because we hypothesize that having this element will probably expedite their pedagogy in terms of inculcating entrepreneurial scientific thinking, or SMET in this case. And of course, beliefs also need to be addressed. I have a 3-minute video here, and this is, please enjoy the video and see whether the SMET characteristics are available in this students' design towards the competition challenge by Luna Lul NASA recently in 2020.
Hi, my name is Jason Kangdisan from Malaysia. I am 9 years old. Today I'm going to tell you all about spacesuit lunar toilet. This spacesuit lunar toilet is very mobilized than other lunar toilets.
Teaching GSEN for the past 5 years. A lot of people, they thought that GSEN is a very special kids or very talented, the prodigy, know everything and then just sparks and then get the idea and solve the problems of NASA. Actually, he is just a normal kid. He likes astronomy and he likes all the space things, and because of that, he keep on learning. When he do a lot of hands-on things, at the beginning it also is very clumsy and cannot fix here and there, but he never give up until he succeed in the end. These are the things that he is special about. He never stop learning. He read a lot. He read a lot of books. He go to find a lot of information about space and that. Saw this challenge, and actually GSEN said, oh, he wants to go for it. And then I said, good, let's work on it. So how are you going to solve the microgravities? Because the P are going to fly here and there. He's saying, let's have a pump. Good. Do you know how to make a pump? He don't know how to make a pump, but he know what are the things that can pump. Syringe, he said, use a syringe. Because we have been using syringe for other activities. This idea is not only that he sparked out like that, but because he know how to ask the question and he already have the fundamental science inside it, then he can do it. So every kids actually they are also like that. We just need to give them encouragement. We guide them through and then they will be succeed. So what is the real message that you would like parents and the public to know about this story? What I'm saying is a lot of kids, they have a lot of ideas. Please don't demolish their dreams. If they have some dreams of making things, encourage them to do it. You will never know what they can do. Every parent, we hope the best for the kids. But are we doing the best for the kids? What can you do? Simple. Listen to your kids. If they have the passions to do it, they will be successful in the end.
Okay, I think maybe colleagues have some ideas on what's, how is it related to SMET. If I could just highlight, you mentioned there, read a lot, information, that is the observation part of it. Use the scientific concept. He started with the scientific concept about pumped and being curious, and that goes on to develop the design. My last slides are a little bit on reflection on future work for research, perhaps. Focus on STEM and SMET education. I think STEM education, yes, and SMET will be promoted through school maker spaces. And these are some suggestions. For example, we could look into what motivates a person or the child to have this value scientific creativity or scientific entrepreneurial orientation. We could look at some of the factors and do more intervention to see what's the nature of the program or nature of the thinking process that could actually develop SMET and also scientific creativity. And perhaps, as I said earlier, there's a hypothesis that scientific creativity could correlate with entrepreneurial science thinking. And finally, the change has to come from the teachers, whether in non-formal and formal situation, towards practicing these concepts. So thank you very much for listening. And Chairman, that's all from me, my presentation. Thank you.
Lilia Halim, thank you very much for, again, welcome to Turkish
thank you.
Turkish audience. For Turkish audience, on behalf of the Turkish audience, welcome. You prepared very nice presentation. You gave too much effort. I saw your presentation. Really, you gave too much, I believe, time for preparation. Now we are waiting questions, our audience.
Okay.
Then we will give the speech for Rachel for her speech.
Yes, welcome. Thank you very much.
Yeah. First question I want to ask.
Yes.
What are your teachers' attitudes toward STEM activities and integration of the STEMs in the curriculum, in your curriculum? Is there any negative attitudes toward this new approach?
Initially, they were thinking that STEM is what they have done before. Most probably because of the form of STEM integration. If you remember, STEM 1.0, STEM 2.0, they have done that. But if you were to talk about integrated STEM, it's totally a different kind of thinking and pedagogy involved. But the Ministry of Education has provided some documents, some guidelines on how to implement them at school. We also have STEM Education Center. We have that in Malaysia. It's under the purview of Ministry of Education, and they are doing a lot in training the trainers, so that the main trainers will go down to school, and their focus is also on integrated STEM and inquiry learning. So I think the change in the perception that is better now. They are changing towards towards adopting that concept.
Thank you.
You're welcome. Okay.
The other colleagues, you can ask question, please.
May I ask a question?
Yes, please.
Yeah, Dr. Halim, this is Mustafa Sozbilir from Atatürk University in Turkey. Thank you very much for your presentation. It is very nice and enthusiastic. I'm just wondering how practically applicable the STEM practices in the schools in entire Malaysia, or it is just practiced in some of the very specific or very special colleges or schools or other places, but it is widespreadly practiced around Malaysia or not?
Good question, Prof. Mustafa. That's the reason when I started presenting just now, if it has to be done systemically. So it has been done through the formal curriculum, in which we have reviewed our curriculum to some extent, and in which we have a subject matter called design technology subject matter. So that's where all the 15 years old students will be taking the subject. So it has to be done at school, and that's where STEM is being infused in the curriculum. At the same time, schools are going into competition, STEM competition, with the sponsorship of organizations, NGOs, and they have a lot of support from there. But again, competition only involves certain students. So it is important to have it infused in the formal curriculum. And again, I would say it has been done by the MOE in providing guidelines, as I've shown earlier, on how to do the STEM pedagogical approach. Some schools may do more. Some schools will probably, if it's in the curriculum, they will do it. Yes. Thank you again to you.
Evet.
If anybody has questions, they could.
Is there any question?
Me or,
Yes.
Burak hocam, sesiniz gelmiyor.
Dr. Halim, do you see the chat?
Yes.
One of our followers, I
Yes,
think,
I do.
have a question.
He says, Prof. Chapney, I also wonder your opinion for the application of SMET in Turkey. That is Prof. Salim? Yes?
No, about that one. Do you think that individual efforts of parents and teachers are enough? Yeah. Miss Gizem Yapar Söğüt asked. The question is, do you think that individual efforts of parents and teachers are enough for the success of 9-year-old child?
So it is, okay. Do you think that individual efforts of parents and teachers are enough? All right. Okay. Obviously, when we look at the ecosystem of education child. If you the child is in the middle, and of course the support system around the child will help. So if you have the teachers only, it will not be enough. The parents have to be involved, the community, as well as other, as well as support from the state. So if it's in the case of that 9 years old child, he have got the support from the parents, and Discovery Center is not part of the formal curriculum. It is something extra where the parents would send not only to such a center, but we also have a public non-formal science learning environment. So the question, the answer is yes, you need a huge team support to ensure a success of a similar to that 9 years old child.
Thank you, Dr. Halim. Now we are a little bit above from the time, and we will continue with Raquel's, Dr. Raquel's presentation. Dr. Raquel, the microphone is yours. Thank you.
Thank you very much. And thank you, Professor Halim, for your comprehensive and very, very profound lecture. It helped me a lot in continuing my own lecture. So I will share the screen.
Thank you.
And hoping that, okay. Is it okay?
Yes, Dr. Naman, it's okay.
So I listened very carefully to your lecture, Professor Halim, about STEM, and I picked up one of the components which you mentioned, and it is inquiry-based approach to teaching and learning science. I will be more specific, and I will talk about this component only. So as you know, I'm coming from the Weizmann Institute of Science, which is a research institute and has into it a department of science teaching, science learning. And the Weizmann Institute is a very well-known institute with a beautiful gardening, and you are all mostly invited to visit us. And first of all, I would like to thank everybody, to thank Professor Sally and Professor Zotzbilar for inviting me. I'm very honored to take part in such an important and prestigious meeting. So as I mentioned, in our department, we are dealing with all the components of science education, namely curriculum development, implementation, research on students, teachers, curriculum, cognitive, affective, whatever, and professional development. You can see our publications on the web. I picked up the inquiry because it's always very much advocated, also by the National Science Education Standards in 1996 and in 2012 as well. But I prefer the citation from 1996, in which inquiry is categorized as learning through inquiry, teaching through inquiry, and science and inquiry. It is a multifaceted activity that involves making observations, posing questions, examining books and other resources of information, planning investigations, predictions, communicating the results, and so on. So what do we define by inquiry skills? What do we include into it? We include asking appropriate questions, findings and synthesizing information, monitoring scientific information, designing investigations, drawing conclusions. And moreover, inquiry skills are highly dependent on the student-student and student-teacher interactions and directly affect the learning environment. If we are looking at, is it clear, because I have here many signs, is it clear what I show? if we are looking at inquiry type experiments and at students' activities, we can see that it consists of so many components, hypotheses, observations, small group discussions, conclusions, and defining a research question. So, I would like, of course, as I mentioned before, to talk about inquiry skills, but to focus on asking appropriate questions, as we cannot deal with all these important components in 20 minutes and not even in 20 hours. We need it's a whole enterprise. So I will try to do something a little bit profound about asking appropriate questions. And why do I want to emphasize this point? Because it's one of the thinking processing skills which is structurally embedded in the thinking operation of critical thinking, creative thinking, and problem solving. And we can, if we listen to Nobel Prize winners and to eminent researchers, we always hear Einstein said that when he came home, his mother asked him, "Did you ask today a good question?" Which we are not sure if it was Einstein, because then they tell the story about another eminent researcher and so on. So the good mother who pushed her kids and who encouraged them to ask good questions. How should we convey this? How should we do it? Again, by trying to explain a phenomenon, and then it raises questions. By exploring the nature of science, what is going around us? Why does it happen? Why does in our body we have only chiral compounds? Why? And why when we synthesize them, it's a racemic mixture or so on. Trying to explain a mystery, which we don't know how to refer to it, conducting open-ended laboratory experiments, critical reading of an article, argumentation activities, and so on, many other species. So, in asking questions, we are referring to a mystery. In my talk, where I will refer to asking questions in conducting an open-ended experiment in the laboratory, and to asking questions in critical reading of an article. Actually, I will give 2 examples, not 3. The first one stands for itself, and the 2 others are parts of one study. So, asking questions referring to a mystery, it was in some project which we had, sponsored by the European Union. It was called TEMI, Teaching Inquiry Through Mysteries Incorporated, with 8 European countries and us and Israel involved in it. It was a very nice one. We had also a few publications that you will be able to look for them due to this reference. When we refer to a mystery, how are we going to stimulate asking the questions? By a challenging story, by an intellectual inquiry, by an experiment, or we should also think, how much time do we want to devote to it? We have other restrictions. We need to face the regulations of the Ministry of Education. We need to cope with our curriculum. Do we have time to look for the answers? What is the target population? Is it related to the curriculum? Or is it just a stimulate for asking questions? Well, it is for consideration of each teacher or each team of teachers or schools to think about it and to see whether it's not too much time consuming, whether it is feasible, and so on. But here is the suggestion, which is very much beneficial. A mystery. An example of a mystery that was given to the students. Yesterday, we had great results at the lab. We explored different kinds of exothermic reactions, measured the temperature versus time, organized the data in a beautiful table, thought about every detail, and afterwards, we became tired and decided to have a break and go to the shore. It was a summer hot day. We met in the afternoon in order to continue our work and opened our notebook. We were shocked. All the data was gone. The margins of the table were there, but the table was empty and some numbers could be vaguely noticed. Something like that, as if everything disappeared. So, what are the questions which the students should raise? Or they really raised when the teacher conducted this experiment with them or told them this story. It depends on the teacher. Where was the notebook during the break? Did it get wet? Was it exposed to the sun? With what kind of pen did you write? Because we know that we have different pens. And can the data be recovered? So in order to know if the data can be recovered, we have additional questions. How does temperature influence, not influences, influence tipo color disappearance? How does the time exposure to high temperature influence the color reappearance? How does the type of color influences temperature disappearance? How does the color disappear? Is there difference between rubbing and heating regarding erasing and reappearing? Can you write with this specific pen on different materials? And so on, many, something like 20, 30 questions. So it is the time to go and teach the scientific background. Maybe the scientific background is not very much in alignment with the curriculum, but still we have in the curriculum concepts like temperature, heat, energy. So it goes together. And even if the scientific background is not exactly explicitly attached to the curriculum, it doesn't matter because it somehow broadens the knowledge of the students and they can see a phenomenon which was not known to them. What have we learned? We have learned that inquiry experiences plus a story, and it was only one example and it was not very much elaborated, may stimulate the skill of asking questions, are especially effective if conducted in the context of or integrated with the concept being taught. It has to be integrated. It doesn't have to be exactly the same. And these components have the potential to enhance students' meaningful learning, conceptual understanding, and understanding the nature of science, the way in which scientists are working, raising a hypothesis, asking questions, conducting an experiment, and drawing conclusions. So this was part of the teaching inquiry with Mysteries Incorporated, which we conducted for 3 years with our students who were very happy about it. I will move to the other example, the example of a study about these two components, asking questions in conducting an open-ended versus an affirmatory experiment in the laboratory, and asking questions while critical reading of an article. So, the goal of this study was to investigate the ability of high school chemistry students to ask questions related to their observations and findings in an inquiry type experiment, in a practical test, and the ability of high school chemistry students to ask questions after critically reading of scientific articles. And of course, we wanted to focus on inquiry type experiments, but we had to compare it to a control group who didn't conduct the inquiry type experiment, because it's very obvious that if you are somehow prepared or taught to ask very good questions during an inquiry type experiments, you will be better in other components. Well, here it's chemistry, but it can be done, of course, in any of the other scientific disciplines, because this is actually STEM. This is the large and the comprehensive idea of STEM, being a literate person, being a person who can have decisions based on evidence, based on data. What did we look for in this study? We looked for the number of questions that were asked by each of the students, the cognitive level of the questions, and the nature of the questions that were chosen for further investigations, because it's not enough to answer questions that refer to one experiment or to one article. We need to go on. That's how the scientists are working, to continue and try to investigate similar questions and see if it works out, if the evidence which we have from one experiment will be validated by the other one. The student population consisted of 6 12th grade chemistry students in Israel, who were also biology students, but never mind. And 12th grade is the last grade of high school in Israel. Age 17 to 18, 111 students. The inquiry type chemistry laboratory group, which was the experimental group, consisted of 55 students, and the traditional type informatory group included 56 students. What were the research tools? It was a practical test, a questionnaire following the enactment of an experiment, which was novel to both groups of students, experimental and control, and a questionnaire based on a primary literature paper. I will elaborate on it later. So the experiment conducted by the experimental group is here described. The students needed to insert 2 solids, A and B, into a plastic bag, mix them by shaking, then pour 10 milliliters of water into the small glass, put the water with glass inside the bag, put the thermometer inside it, measure the temperature, then tie the bag carefully, turn over the glass and let the water completely wet the solids, record observations and answer the questionnaire that is enclosed. This is the experimental group. The control group didn't have 2 solids which are A and B. They knew from the beginning what are the solids. So they needed just to observe and to write what they were observing and what were the conclusions. This was the only difference between the experimental group and the control group. Namely, the control group was the informatory group. They needed just to look and see what's going on. Oh, sorry, I don't know what happened. Something just happened now. I'm sorry. Okay. I will. It's fine. Is it fine?
Yes,
Are
it
you
is fine,
saying
Rachel.
okay? Is it
yeah,
okay?
It is fine now.
No problem.
No problem.
Yeah.
So they needed to write the observations, and after performing the experiment, to answer the following questions. Both groups. What questions do you have after the experiment? Choose one of those questions as an inquiry questions. And there were more than that. For both groups, the control and the experimental, well, we can now actually somehow predict how did the both groups, because one group knew what is A and B, the other one didn't know, but nevertheless, we need to prove it. We need to prove it for stakeholders and show that when you are doing an inquiry type planned experiment, it somehow stimulates your imagination much more than when you know what are the products. And the scientists also don't know from the beginning what they are mixing and what they are doing. Then they needed to read an article which we call a primary article, which is an original scientific article. It is written by a scientist, as it is not adapted and anything published in professional journals. Part of it was, I will read here, it was about the nitric oxide, NO, which it was chosen because the nitric oxide was the molecule of the year, I guess in 1992 or maybe another year. It acts as a single molecule in the nervous system as a defense agent against infections, as a regulator of blood pressures, and as a gatekeeper of blood flow to different organs. In the human body, it is thought to have a lifetime of a few seconds. Thus, its direct detection in a low concentration is rather difficult. The article reports on a design of a new electronic sensor sensitive to small amounts of NO in physiological solution and at room temperatures. The researchers are from the Weizmann Institute, from Tel Aviv University and others. I guess Mustafa, I'm sure Mustafa Zoswiller knows one of them, Naaman Ron. He's also from the Weizmann Institute. And this is written in European journal. So both groups, the control group and the experimental, they needed to read the article and answer a questionnaire, write down the questions that they would like to ask after reading the article, and from the list of questions to select the most interesting one to investigate. The data analysis was done by the questions were presented by the students resulting from the practical test and from the critical reading were validated according to the content validation. And all of them were judged by 4 experts, science educators, who were asked to define them according to low or high order types. Continuing the data analysis was by comparing between the inquiry and the control groups regarding the number of questions that were asked by each student. It's a quantitative, of course, the level of questions posed, high or low, quantitative and qualitative, and the questions that were chosen for further investigations. So what we could see that the 2 groups were compared regard to the mean number of questions asked and number of high level type of each one. T-test analysis and t-tests were conducted. What we can watch that comparing the mean a number of high-level type questions asked by the student in two groups, we see that the control group, if we can see the number of students who asked high order questions were very, very low. It's the brown one, brown or red or whatever. Most of them asked low level questions or questions which are not very, very sophisticated, while the inquiry group did better. If we look at, before it was the number of questions and now it is the high level number of questions. Again, we have the same graphs. That the control group, they asked low level and less high level questions than the inquiry group. They also didn't ask the most high level questions, but never mind, they should exercise and continue with this enterprise. So, for example, what do we mean by high level or not high level? Several students in control groups did not choose any questions, and the questions were low level. Why did the bag puff up? Did the temperature decrease? Something that you can measure very easily. The inquiry chose questions that were of a higher level. What will happen if we insert a different amount of water? Will the temperature increase if we insert another amount of water? Does the amount of powder influence the powder? And more thinking about it, trying to feel much more being engaged into this experiment. Then if we compare about reading the article, again, we have the same number of high order questions per student. We see that the control group didn't have high order questions, while again, the inquiry group had a larger number of questions. We could predict it, as I said before, but unless we have the data, we cannot somehow have an influence of anything which will happen afterwards by policymakers. We need in education, in science education, and we all know it, we need to prove what is expected. It was expected, but by performing this experiment, by performing this study, we could prove it. And following this study, we had other studies also, which reinforced this data. So, again, we can show an example of the high-level type questions of the inquiry group. How is the NO molecule released from the device? This is really something they really want to know. Can the device check the concentration? Can the scientists use the device to detect other molecules, which is expanding the scope of the paper. The students who posed low level was how is the current recorded, which is shown, it's written in the article. You don't need to guess it. Can the detection be used for medical application? It's written in the article. These are not high order type questions. So if we want to conclude, we can see that the students who were involved in the inquiry type experiments were much more motivated to pose questions. Namely, they were thinking much more about it. They were not better students than those in the control group. It was randomly divided, but due to the way in which they conducted the experiment, they were much more motivated to pose questions and devoted more time and attention to complete the questionnaire in order to, they were curious just to find out what was going on. cognitive aspects, the students who were involved in the inquiry type experiment, they improved their ability to ask better and more relevant questions, which is one of the important components of scientific literacy mentioned in STEM by Professor Halim, developed scientific skills and habits that are applicable to other learning situations and to everyday life, we assume and we hope. Now, it's not just asking questions, it's not just a curriculum, and it's not that just the students. And again, as mentioned by Professor Halim, these are the teachers too. It's a complex enterprise. In the middle, there are the policymakers, but we can do what we can do. We can influence teachers, students, and curriculum. And the challenges are big for teachers because they are the key to any successful implementation, to any success of their students. They should get, and therefore, they should get support and a very sustained preparation, scaffolding in any novice or any new enterprise, any new program, especially in inquiry activities. So if we would like to quote Tobin, although it's from 1990, and from then we have a lot of citations. And even a colleague of mine and myself, we quoted something very similar in 2012 and afterwards 1 year ago, but he defined it very well. A crucial ingredient for meaningful learning in inquiry activities is to provide for each student opportunities to reflect on findings, clarify understanding and misunderstanding with peers, and consult a range of resources, which include other students, the teacher, and books and materials. So we should consider it and think about the whole time. It's not just one component, it's a systemic, it is a systemic action, a systemic enterprise, as I mentioned before. Here is, I wanted to show something. It doesn't relate to our lecture. It relates to peace in the Middle East, but I don't think that we have time. If there will be time, I will ask my colleagues and maybe Professor Mustafa Zotzbilar to show it afterwards. I don't want just to take the time from others, but it's very beautiful. And I would like also to tell Professor Halim that I was invited to Malaysia in 2016, and it was a pleasure. It was in Borneo to give a plenary lecture at the ICCE meeting. I enjoyed very much the people and the environment, and I really hope that we all will be able to meet everywhere with no restriction. And that science and science education and inquiry, people who will think and inquire the phenomena of the human being will be able to do it without what's happening with our politicians who are really depressing us and everyone. So thank you very much for listening. Thanks again for inviting me. And I'm looking forward to questions if there are some.
Thank you very much, Dr. Rachel and Dr. Lilia Halim. I hope we will meet in Turkey in the near future.
Yes.
I want to ask first one question, then I will give the audience, they can ask you the question. In Turkey, many teachers, they believe that inquiry or developing inquiry skills is impossible because there is no time. Therefore, they prefer to use exposition teaching approaches. And although many educators or scientists recommend our teachers that learning occurs if you use inquiry approaches or system approaches. But there are very serious resistance in Turkey. What is the condition in Israel?
So, I would like to mention the fact that it's not only in Turkey, it's in many countries and also in Israel. There are many schools that are not using it because it's sometimes regarded as time consuming and we can just learn it by heart. But it became, by our inspector, it became compulsory, and it is 20% of the matriculation score.
Yeah.
You know, well, they need to conduct these kind of experiments, open-ended and inquiry, and also other inquiry activities. And if they don't conduct it, they don't get their matriculation score at the end of the 12th grade. So they are forced to do it. And when I say forced to do it, it makes me feel very bad, because what I think that maybe it's time consuming, but it's also time earning.
Yeah.
Because if you teach your students to think, then you can teach afterwards other subjects much easier. So we slowly with our Center for Chemistry Teachers, and we have other places where we can speak out our mind, and with our professional development activities, which I'm heading it for 20 years and more, we try to always to show the teachers and to convince them that sometimes what is time consuming is time earning. Then you can also ask your students to study something by themselves, to study it first at home and then coming to class and discussing it. We call it an opposite class. We try to do our best. We don't always succeed, but we believe in it with all our heart. And I must tell you, Sally, you are not alone.
Yeah.
We hear it also in our place. Why do they force us to do it? But we need to be persistent, and we need to continue, because this is really, really our future.
Yeah. Thank you. Mustafa Hocam.
Yes, Rachel, thank you very much for this enthusiastic talk and an encouraging view about people, why they should go through the inquiry-based teaching, because as you said, it is time consuming, but it is also time saving in terms of the skills that the students gaining. I'm just wondering, not just in terms of the school making it compulsory in the schools, but how do you persuade or train your teachers to be able to skillful to apply those kind of inquiry-based teaching activities in the school or in the university or anywhere else? Do you have any systematic teaching or training program for these kind of activities?
Yes.
Thank you.
Yes. So here I feel good, because as the chair of the National Center of Chemistry Teachers, we have a lot of activities. We have a journal, we have meetings, and we have ongoing long-term professional development courses during the year. When teachers are coming, let's say we have 3 or 4 courses like that, and teachers are coming once in 2 weeks for 4 or 5 hours in the afternoon, in order to get, I don't like the name, trained, prepared for a certain subject. And one of the subjects is conducting inquiry type experiments or conducting inquiry type activities, not only experiments in the laboratories, critical reading, or even in a classroom. So these are courses which are regarded as being 112 hours periods a year for a teacher. They get a certificate, and unless, especially in this type of let's say subject, they needed to take to get a certificate before starting to teach it, because otherwise they are doing it very differently and they spoil it. One experiment can take 6 to 7 classes, 45 minutes each, in order to not, it's not that doing the experiment in 10 minutes, but all the discussions, the argumentations, the conclusions, and doing again an experiment, it takes a lot of time. And if they don't know exactly how to do it, it's a disaster. So they needed to get prepared. So after they get prepared, they get more self-efficacy doing it, ownership, because they also comment about the experiment, they add their own experience, and they go, oh, we want to do this experiment, we want to disseminate it. This is the way in which we are operating. But if we will continue like we continue now with what's going on in our country, I don't know if there will be a continuation of sponsoring all these activities. We hope that we will do, because almost all of us work like volunteers in this now. And what I want to say, more than that, I believe, and we all believe, that it's not only education for science, it's education through science. So we're educating people to be critical thinkers, to be critical about what they see and what's going on. And if we have a lot of them, then maybe we'll have a better world. And that's also we are talking. I myself, I am integrating a lot of it into my lectures, into my workshops, a lot of the general knowledge, and not politics, but values, ethics, all that should be inside.
Thank you very much. Is there any more question for Dr. Lilia or Dr. Rachel? We got a few minutes more.
I want to ask Dr. Halim.
Yeah.
If I represented correctly one of the components of your STEM.
Yes, inquiry. The inquiry learning, questions asked will definitely lead to value-added, innovative solution to the problem. I agree. And may I add, in this COVID-19 pandemic, I think teachers are being forced to see what are the most important thing to teach, or competencies, and what can be left out, because often teachers would think that they need to finish the syllabus, and therefore inquiry it will take a long time. But I hypothesize, or I think with this COVID-19 situation, it will ask the teachers or even the curriculum developers to reflect on how much of information or competencies or skills that need to be included in the curriculum and implemented. Perhaps then inquiry will be adopted easily. What is your view, Dr. Rachel?
It was fantastic what you said, really. I thought about it, but I thought I won't have time and I forgot it. But it was right in time. We now today see what is important in teaching science. Really, you elucidated it in a perfect way, and I thank you very much, because we are really living in a very peculiar time, and we should